So, hello everybody, I'm John Southworth, and the idea of this screencast is that I will show you how to fit the light curve of an eclipsing binary star system using my light curve code called JKTEBOP. And now, if you are listening to this, I'm going to assume that you have some understanding of eclipsing binary stars, but you aren't familiar with the code. So the code itself is written in Fortran. It's a single file which you can download from my website, and then you can install it in whichever way you want. That depends on what kind of computer you're running, and then you can run it to model the light curves of eclipsing binary systems and also transiting planetary systems. And what I'm going to do now is take you through the solution process for one of my favourite eclipsing binaries, YZ Cassiopeiae. So we'll start with looking at the data. So if I open up a text file now and take a look at the data file, this is it. So this is a light curve of YZ Cass, which has been taken from the NASA's Transiting Exoplanet Survey Satellite, or TESS. And in this data file you'll see three columns. The first one of these gives the times of each brightness measurement, and that's given in Julian date, but I've knocked off these 2 and 4 at the start of each one of these, just so I don't lose precision in the computer code later on. Second column is differential magnitude. Now that is not fluxes, it's differential magnitude. So if your light curve code is in flux, you need to convert that into magnitude units. And the third column, this one here, that is the error bar on each of the data points. However, from experience, I know that this satellite tends to produce error bars which are too small, so I'm going to tell JKTEBOP to forget those error bars, and I'll just type no error in the top of there. You can type anything you want there, which is a letter and not a number, and that will have the same effect. So that's what the data file looks like. What's more interesting is what the data look like when you plot them. So for plotting, I'm going to use this Linux stalwart called GNUPLOT. Now JKTEBOP doesn't do any plotting itself. Input and output is all by ASCII files. So therefore you'll have to do that kind of thing yourself. That makes things a bit simpler in many ways. So to start GNUPLOT, I type GNUPLOT, like that. I'm going to open up my terminal here, and the next thing I want to do now is just plot up the light curve of YZ Cass. So plot YZ Cass.dat. Produce this window here. Let's just resize that a bit, make it a bit clearer. And you'll notice several things here. Firstly, there's a legend which mostly gets in the way, so I'm going to type unset key to get rid of that. Secondly, the points here are quite large, so I'm going to make those smaller. So set point size 0.5. Thirdly, as you'll see, the eclipses are when the star gets fainter, but they are currently pointing upwards, whereas we want them pointing downwards. And that's simply because the light curve is in magnitude units. So I'm going to change that by doing set y range brackets reverse. And so now if I replot, you'll see this is a stretch of light curve I've decided to work with. It's about 11 days long, and you see the quite nice primary eclipses here, and the secondary eclipses between them. These eclipses are total, which means this system should be very easy to model. Okay, so now I've done that, it's time to actually start the modelling process. So I'm going to assume that you've got JKTEBOP installed, and therefore you don't need to worry about that. I've got it installed in my system here, so I just type JKTEBOP in my command line, and it shows that it's working, and it just outputs a little bit of stuff to tell me how to get going with the code. What I want to do here is start with a new fit, so I'm going to ask for new input file. So JKTEBOP new file. So now it will ask me the name of the file to create. Because I'm looking at this system called YZ Cass, I'm going to call it yzcass.in. Next, it wants to know which task I'm going to do out of the 9 available. And I'd advise most people look at this to just skip straight to task 3. That is a standard basic fit. So now it's written a new file for me, so let's have a look at that. Here we are. So this input file is just a pile of text, and we have to add in some parameters on the left hand side, and which ones to add in are given by these little comments down the right hand side here. So I'm going to start by telling it which task to do. As I said, we want to do task 3. Next thing I want to do is specify the integration ring size, which sounds complicated, but mostly we can just put that at 5 degrees and forget about it. Now, integration ring size gives us the quality of the numerical calculation in JKTEBOP. I tend to find it doesn't make much difference to anything, So I'll stick 5 here. If you are worried and you want a really precise light curve, you could knock that down to 1. That will just mean that the light curve code will take a bit longer to run. Well, nearly a factor of 5 longer to run. Okay, so the next parameter is the sum of the radii. And when I say sum of the radii, what it means is the fractional radii, which is the radii of the stars divided by the semi-major axis of the relative orbit. So that means that the sum of the radii should be somewhere between 0 and 1. 0 for very small stars in a big orbit, and 1 for when the stars get very, very close together. Now, JKTEBOP will only cope up to about 0.4 or so, but in this case, these eclipses are relatively short compared to the rest of the light curve. And I'm going to guess that the sum of the radii here is probably somewhere around about maybe 0.2. Next, the ratio of the radii. Now that's just the radius of the secondary star divided by the radius of the primary star. And we can see here that we have total eclipses, and that normally happens when one star is quite a lot smaller than the other. So in this case, I'm going to guess 0.5. We can fiddle with that later on to make it work. Next, the orbital inclination. Now, for eclipsing binary star systems, the inclination is usually somewhere near 90 degrees. Could be as low as 17 cases. This is a case, I think, which looks like it's got quite a high inclination, so I'm going to stick 88 degrees in there. Next, mass ratio. Now, this doesn't have much effect on the results. It only really affects the importance of the ellipsoidal effect outside the eclipses. And in this case, I think the simplest thing to do is just to say that we'll go with assuming that stars are entirely spherical. So therefore I put a negative number, that's sticking -1, and the stars will be assumed to be spheres for all of the light curve code. Next, orbital eccentricity, in terms of e cos omega and e sine omega. Now this is, we think, a circular orbit because the secondary eclipse occurs pretty much halfway between the primary eclipse, and it's also pretty much the same length. So I'm going to stick 0 for that, and 0 for that as well. Next, gravity darkening. Now that's an effect where the part of the star with the lowest surface gravity will be a bit fainter than part of the star with a higher surface gravity. It's not very important for well-detached systems like this, and I've also set my stars to spherical, so they'll have the same surface gravity all over, so I can basically ignore this parameter. So stick that to 0 for both stars. Next, surface brightness ratio. Those of you who are familiar with blackbody physics will know that the surface brightness ratio is a ratio of the brightnesses of two stars at the midpoint, and that depends on temperature ratio to the power of a quarter. Now the surface brightness ratio pretty much is determined by how deep the primary eclipse is compared to secondary. In this case, the secondary looks to be maybe half as deep as the primary, so stick 0.5 there. That would probably be perfectly fine. Next, third light. Now this is an option to include additional light for another star, which is included in the light curve, but isn't one of the eclipsing binary stars. Now I'm going to set that to 0 now, but in general, especially with space missions, there might be a small amount of third light, so it's best always to try and fit for that, which we'll be doing later. Next, limb darkening. Now JKTEBOP has got quite a range of limb darkening laws. I'm not going to go through them now. Let's go with the half decent one. Let's go with quadratic. So I'll put quad. The quadratic limb darkening law is one of the 2 parameter laws. It's definitely not the best one, but it is quite widely used. Okay, next I need the limb darkening coefficients for both stars. So the linear coefficient, I'm going to set to 0.3 for both stars. If I was going to be doing a detailed fit, I'd get a better set of predictions from theoretical models, but right now just guessing 0.3 for everything is going to be fine. There we are. Next, the reflection effect. Now that's an effect where the side of the star facing towards the other star gets heated up by the other star and gets a bit hotter. And the coefficients of that can be included in the fit here. So I'll stick that at 0 for the moment, but we can fit for those later on to get a better fit to the light curve. Next, the orbital phase of the primary eclipse. That should always be 0 really. I allow an offset if necessary, but I very, very rarely use that. Light scale factor. That gives the brightness of the system outside eclipse. So it should be pretty much this level here along the end, which is round about 0. So I'll stick to 0. I've already changed it to 0, that's why it's round about 0. Next, the orbital period of the eclipsing binary system. Well, before we do that, let's have a look at the reference time of primary minimum. And so I can measure that straight from the data here by looking at the time that this primary minimum occurs. Now with GNUPLOT, one of the slightly irritating things is it doesn't give that many significant figures. So what we're going to do now is plot the light curve just by subtracting 58,000 from the timestamp of each one. And now you'll see here we have fewer significant figures down here, and I can zoom in on this bit of the light curve and think, well, the midpoint of that prime eclipse is going to be something like 58,820.17. So 58,820.17. Fine. And next I need the orbital period. Now the orbital period is just the time between one and the next primary eclipse. Could do it in secondary eclipses. So if I measure the time of this eclipse and subtract that eclipse, that should give me the orbital period. So this is going to be, this time's done by 824.64. So that's going to be 4 days, 0.47. So 4.47 days is the first guess at the orbital period. And we'll fit that better later to make it better. So that's all the parameters we need. There's 4 more things we need to do as well. We need the files for input and output. Now the input file is called yzcast.in. That's already here. The data file is yzcast.dat. Next, the output parameter file. Now the output file from JKTEBOP, one of the output files is the parameters. It gives you the input parameters and the output parameters, various other stuff, and that's the most important file. So I'm going to call it yzcast.par, where par is for parameter. Next, it will also produce an output file which has the model fit for every single data point that I want to fit. So I'll call that yzcast.out for output file. And finally here, the next one is yzcast, the model light curve fit file. Now that's a light curve just evaluated at a large range of times, or in this case orbital phases, just for good plotting. So I'm going to call that yzcast.fit for it being the best fit. Okay, so we have our input file now. There's a pile of zeros here, you'll notice, which I've just ignored for the time being. Those tell JKTEBOP which parameters to fit for and which to leave fixed. And the first thing I'm going to do is leave them all fixed, just to see how good the light curve looks like without changing anything. So there we are. So what I do now is run JKTEBOP. JKTEBOP. Now give it the name of the input file, yzcast.in. And it's produced some new files. It's around 8,000 data points, and it's not done a fit because every single parameter was fixed. So let's see how good a fit that is. So if I go back to my plotting yzcast here, I'm going to do plot yzcast.out. So that's going to give the information from the output file using columns 1 to 2. That's where the data are. They're just repeated from the input file. Now I also want to plot the fit file, so the fit to this, which means I want yzcast.out, again the output file, and I want to now plot column 1 versus column 5, because that's where the model is. I want that to be in lines. Okay, so let's try that. And that is already an extremely good fit. Wow, that was better than I was expecting. I usually expect to see a bit of a difference. And so looking at this, we can immediately say, well, that's a really good starting fit. I can just go straight to the fitting process from here. So let's do that then. So what do I want to fit for? Well, the fractional radii, particularly some of the fractional radii, they govern essentially how wide the eclipses are. We do need to fit for that. That's one of the most important parameters. Then the ratio of the radii, we definitely want that as well. Next, the orbital inclination. Yep, that's something we should be fitting for. Mass ratio, no, I'm going to fit that, leave that at -1. Eccentricity, leave that at 0 for the time being. Gravity darkening, ignore. Surface brightness ratio, I do want to fit for that. You'll notice here that particularly in the primary eclipse, the model isn't quite as deep as the actual primary eclipse, so that definitely needs to be adjusted. Next, third light. That is something which I can't guarantee is not there, so let's just fit for that to make sure. Next, limb darkening. Now, because these stars are totally eclipsing, I should have some information on the limb darkening in the light curve. So I'm going to fit for limb darkening coefficient for both stars. Just one of the coefficients, not both. That's because for a given star, the two limb darkening coefficients are very strongly correlated, and so it's usually really difficult to fit for both of them. So I fit for one limb darkening coefficient for each star instead. Next, reflection coefficients. They will govern what goes on outside the eclipse, so I want those. Phase shift, leave fixed at 0. The scale factor, I want my model to be able to move up and down to fit the data, so let's fit for that as well. And finally, I want to adjust for the orbital period and the time of the primary eclipse. So that's quite a few parameters to fit for, but it should all come out quite nicely because this is a very well behaved system. Okay then, so I just recall the previous command, I run JKTEBOP again. There we are, and it's complained. That's because I've set it up to refuse to overwrite output files that are already there. So if you have output files and you don't want them, you've got to remove those by hand first. But in Linux, that's completely straightforward. Just do rm yzcast.par, yzcast.out, yzcast.fit, issue new command, JKTEBOP yzcast.in. I've misspelled that. And that should be fine. So I let that go, and this command then has removed the old output files that I didn't want. Then it's run JKTEBOP for me, and I can just recall that command and rerun it every time I want to do this again. So it's done 26 iterations. You're seeing it pretty fast, and I'm expecting now to see quite a good fit. So if I replot the fit, you'll immediately see that's actually an extremely good fit to the data. So the next thing I can do now is I want to put some residuals on this plot here, just because that's a very good way of diagnosing any remaining uncertainties in the model. So for residuals, I want to have, let's plot them at a magnitude of 0.4. And let's now plot the residuals. So I want yzcast.out using 1 to 6, because column 6 in the output file is residuals. Oh, and I forgot to add 6 to that, add 0.4 to that. There we are. So those are residuals. Now the next thing I want to do actually is looking at those residuals. They seem quite small, and I really would like to magnify that a bit. So I'm going to take those residuals, multiply them by 5, and you'll see now there's a little bit of wibbling on going around through the light curve. But that's not particularly major. These kind of slow trends here are mostly due to imperfections in the spacecraft data. They're not a problem with the model, so right now I'm going to leave those as they are. Now the next thing we could do is look at the results from JKTEBOP. So I will start off by opening up the parameter file. Here we are. This is what it looks like. So it starts off with a set of results, well, set of input parameters. It repeats those for us, and then it goes to the output parameters, and it gives me the best fitting number for each one of these and an uncertainty. Now the uncertainties here are not reliable because they are formal errors from the covariance matrix. They're not the best way of doing things, so JKTEBOP has other ways of getting better error bars. I'm not going to go into that now. If I skip a bit further down, and it also tells me the fractional radii of the primary and secondary star, the light ratio, the impact parameter if you want that, and then also how many data points, how many fit parameters were, and the residuals, the size of residuals, which is 0.9 millimag in this case. And finally, just a little bit of help, it tells me the 2 highest and 2 lowest values of the residual in the light curve, so I can diagnose if there's one data point which is really way off compared to the rest. In this case, there aren't really, so that's not a problem. Next, let's have a look at the output file. yzcast.out. This is labelled, so it should be quite obvious. Here are the data that go in the first place. Time, the light curve and magnitude. The error bars were not included, so they come out at -1. That's just the way the code deals with them. Then it's calculated the orbital phase, where phase 0 is primary eclipse and phase 1 is the next primary eclipse. It's given me the predicted magnitude for the model of the light curve at that time, and then it's given me the residuals of the fit, that is the observed brightness minus the model brightness, and that is what I've just plotted here. So that's the out file. Then finally the fit file. Take a quick look at that. This is more complicated than it needs to be, but you can ignore most of the columns here. The only columns you really want to know are the first two, the orbital phase and the magnitude of the best fitted model at that orbital phase. And there's lots and lots of different phase points going from 0 to 1, so when it's plotted, it looks nice and smooth. Right, so there's another thing I want to do now, before finishing off, and that is, instead of plotting versus time here, I really want to plot versus orbital phase, so I get more of a close-up in the primary and secondary eclipses. And the best way to do that is to start maybe from here, and go maybe up to there, and so that requires me to plot these things up twice, one from phase 0 to 1, and then another one when I'm taking one off the phases to shift everything left as well. So let's just do that. So I want to plot yzcast.out using, I want 4, because that's the orbital phase column, to 2. I'll start off with that. So that is my light curve expressed as a function of orbital phase. And I want to plot from phases minus 0.25 to 0.75. So there we are. Now the next thing is I want to have the first half of the primary eclipse there as well. So I need to do YZCast.out using $4 minus 1 to 2. So I'm plotting column 4, but I'm taking a number of 1 off each of the values there against column 2, and that will fill in the first half of the primary eclipse for me. So far so good. Now the next thing I can do is plot YZCast.fit. So that's the output finer sampled fit file, and I will plot that in lines. That gives me now a little light blue line going from here. It's not necessarily going to be easy for you to see, but it is there. Now I've not got it on the left hand side here, so I want to add that as well. So I need using $1 minus 1 to 2. So what that means in GNUPLOT is I'm taking column 1, that's the $1 there, I'm subtracting a number 1 from it all, then I'm plotting it versus column 2. I want to do that with lines again. And now you might just be able to see the best fit is also evaluated in this bit as well. And as I said before, we want to do residuals. So I'm going to do YZCast.out, because that's where the residuals are, using 4 to 6. So that's phase versus the residuals. I see it's up there. So the next thing I want to do is say I want my residuals to be offset by plus 0.4. So I do like that. And it's now moved them down to below the light curve. And of course I also wanted to do, I wanted to multiply those by a factor of 5 so I can see much more what's going on. So there we are. And of course I want to fill it in on the left hand side as well. That should do it. And there we are. And the final thing is I would like a nice little line along at 0.4 just to show where the residuals should be. And there we are. And that is the way of fitting the YZ eclipsing binary system. There's other more complicated things to do, but I will leave that for another screencast. So, thank you for watching.